The Rockwell Semiconductor facility located in Newport Beach, California, is responsible for the majority of in-house semiconductor wafer manufacturing. The wafer fab is a 240,000 square foot, two-story concrete and steel structure housing Class 1 and Class 10 clean rooms and equipment. These assets are valued at over $1 billion. Located on the roof are critical environmental control systems that support the clean rooms below. The roof equipment, as well as the sensitive manufacturing tools within, must remain operational at all times, as the clean rooms are in production status 24 hours a day, 7 days a week. Therefore, it is imperative that all practical measures are implemented to ensure that there are no interruptions to the continuous operation of this facility. In the true tradition of a high-technology corporation, Rockwell has decided to implement a base isolation system in lieu of a conventional seismic retrofit to minimize damage and business interruption in the event of an earthquake. Located around the building are various attached structures and critical utilities which will have to be decoupled and isolated along with the main building to allow for displacements during an earthquake. These include a hazardous materials storage and bulk distribution building, process nitrogen, acid and solvent waste, deionized water, electrical, and HVAC. Because of the vast number of these utilities and other operational constraints, it was decided to approach the project from the south side. The building expansion shown here was constructed with a base isolated foundation in anticipation of its connection to the main building. This cross-sectional view shows how a seismic event can affect the building and equipment in its current non-isolated state. With a base isolation system, earthquake forces on both the building and equipment will be significantly reduced. Additional columns will be installed at the exterior of the building to reduce horizontal displacement, providing additional protection to the manufacturing environment. This graph shows the effect on the second floor, non-isolated acceleration. Then, after base isolation. Here, we see the effect of the acceleration on the roof structure, non-isolated, and then with a base isolated system. Construction work is screened from view and limited access is maintained by a 10-foot-high fence around the project staging area. Access to the project is created by the excavation of a 30-foot-wide road along the south side of the building. Ramps at each end will channel trucks, material, and equipment to and from the site. The first step in construction will be the excavation below the building. It will progress in slots between the rows of existing footings using two simultaneous crews. Using a combination of as-built information and new survey data, existing utilities such as sewer lines will be located before underground excavation begins. Then, relocated into adjacent bays to ensure uninterrupted utility service. The initial excavation will be 4 feet 6 inches below the existing footings with shoring put in place to hold up the first floor slab. The use of specialized excavation equipment will reduce noise and vibration to minimize impact on the occupied facility. To protect the building from excessive vibration, a vibration monitoring system, or VMS, will be installed before any construction activity begins. The VMS will consist of vibration sensors placed underneath the second floor photolithography areas and at the photomask area on the first floor. These sensors will be tied to on-site computers which will sample the data to ensure that vibrations are within acceptable tolerance levels for production. In the event that construction vibration approaches unacceptable levels, the VMS will send a stop signal to the work area until the cause of the vibration can be found and eliminated. Upon completion of the first pass of excavation, drilled piers will be installed at the corners of each existing footing. This work will progress down each of the excavated slots close behind the initial excavation. First, specialized equipment will drill a 2 feet by 18 feet deep caisson. Then, a rebar cage is installed, and the caisson is filled with concrete. This creates a platform for the installation of the steel underpinning beams. The underpinning beams, jacks, and spacers are installed beneath the existing footing. The load of the building is then transferred from the soil beneath the footings to the piers. First, the existing columns are core drilled and steel reinforcing is installed and epoxied in place. Then, the steel beams are installed and a rebar cage is fabricated on top of the existing footing. A rebar mat is extended along the beams. Pressurized concrete is pumped into the area above the footing, encasing the steel beams and rebar reinforcement. Finally, shotcrete is spray applied to the mat above the beams, creating a new 5-inch slab that provides additional lateral support. Completion of the new slab and beam foundation allows the temporary shoring to be removed and the second phase of excavation to proceed. The remaining earth between and below the existing footings is removed to the final depth of 13½ feet, utilizing both hand and machine excavation. New steel reinforced concrete footings are poured at the final depth, which will be used to support the base isolator assembly. The bottom of the existing footing is core drilled and the upper bearing plate is bolted in place. The isolator pedestal is steel reinforced, the lower isolator bearing plate installed, and then poured with concrete. The isolation assembly is now ready for the isolator installation. The base isolation system installed on this project was custom designed to meet two distinct performance functions. The first function was to support the weight of the building, ensuring structural integrity for day-to-day operations. The second was to provide horizontal flexibility and energy absorption in the event of an earthquake. The horizontal flexibility allows lateral movement of the supported structure and will also act as a spring, ensuring that the building returns to its original position. The energy absorption dissipates the seismic energy produced by ground shaking within the isolator itself, rather than transferring the energy throughout the structure. In effect, the base isolators act as state-of-the-art shock absorbers, which can significantly reduce the seismic energy demand acting on the structure. These performance properties are achieved by designing and producing base isolators with a unique combination of being stiff vertically and soft horizontally. This is accomplished by using a sandwich construction of alternating horizontal layers of special-purpose rubber and steel plates with a centrally positioned energy dissipative core. During seismic activity, the core will transform the energy associated with ground shaking into harmless heat, limiting the horizontal motion the structure will experience and minimizing the potentially damaging energy transmitted to the support structure. The final phase of production includes a stringent quality control testing of each and every base isolator. The equipment utilized for this testing puts the base isolators on their sides, 2 at a time, and can place up to 2,000 tons of compression, 450 tons of shear, and 30 inches of shear displacement. The base isolator is now installed and aligned. Bearing plates are grouted and lower bolts secured. A flat jack is placed between the isolator and upper bearing plate. Upper plate bolts are loosely installed. The jack is expanded and the load is transferred to the isolator. Now the upper bolts can be tightened and the jacking beams removed. The concrete piers will now be removed and the base isolation system is now complete. A concrete moat is built completely around the building, allowing the base isolated building a maximum of 2 feet of movement in any direction. The scope of this project is realized by the amount of materials moved during the 2-year project. 75,000 cubic yards of soil will have to be excavated from below the operating facility. Over 1,700 steel beams and 2,000 cubic yards of high-strength shotcrete will be installed to support the first floor slab. 12,000 cubic yards of concrete will be installed to create a new footing and grade beam system below the existing footings for support of the isolator system. 1,500 cubic yards of concrete will be installed to create a moat around the existing structure in order to allow the building free movement in relation to the earth during a seismic event. 235 isolators will be installed capable of 2 feet of movement in any direction. 500 tons of structural steel will be installed to stabilize the roof structure. Seismically upgrading the wafer fab using base isolation and state-of-the-art construction techniques enables continuous operation during all phases of the upgrade. When completed, the structure will work with rather than against the forces of nature during seismic activity, protecting billions of dollars in assets and Rockwell Semiconductor Systems' competitive edge in the marketplace.